Okay. Okay. So yeah, let's just start. So yeah, hi guys. Welcome back. Yeah. So this is a session on basically our second session. So the topic is will be on what's gradually varied flow, rapidly varied flow, and hydraulic jump. Yeah. So before we start, please fill in the attendance for those watching the recording or on Zoom or here. Yeah, just for admin purpose. Okay, but anyways, uh, what else? Oh yeah, just some context first. So for this topic, right, it's not included in quiz two. Okay, just for you to know, so for the one watching also. So the topic will be not in quiz two. Quiz two will be on hydrology. However, this topic will be in your finals. Yeah, I'm doing it now because if I do it after hydrology, then it'll be quite packed in your finals. So yeah, I see there's only like 13 people here. It's okay. We can watch the recording, but yeah, yeah, I better do it now rather than later. But okay, just for context lah. Okay, so just to recap a bit, so part one, right? So from week one to recess week, it's on hydraulics. So we've covered uniform flow. So the yn equals to wait, no, this one is the Manning's formula lah, Manning's equation. Yeah. Then we have covered the EY diagram. The EY diagram. So this one is your topic for quiz one, right? So now we're going to the second half of hydraulics, which is these three. Okay. So I think the most important part here, right, is actually the water profile sketching. And yes, it will take a while to explain it. But once you know, right, it's actually quite okay, quite easy. Okay. So yeah, so let's just do it lah. So basically, right, let's start with the qualitative gradually varied flow. Okay, so basically, right, if we have a change in condition, um, so let's say there's a slope change or something, right? The water, right, will not, okay, like in uniform flow, right? If you recall, right, if there's nothing, if there's no obstruction, right, the flow on the river will be simply yn, okay, the normal depth. However, in this for this part of the course, right, there will be obstructions or change in conditions. So for example, right, we have a mild slope, a steep slope. I'll explain what these are later, but anyways, the water will be looking something like this. So it will be curvy like this. So this one is M2, this one is S2. Again, I'll explain this in a minute, but yeah, basically for GVF, right, the water profile is not straight, okay? It's curvy, okay? So how do you know how the water behaves, okay, in this change of condition? So there are a few rules. So as you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's a lot, but don't worry, I'll explain it one by one. So yeah, let's just start with point number one. Okay, so let's say you are given a river like this. Okay, this is the side view. So side view. Okay, so when you want to start sketching the water profile, right, you must first determine what we call the bed slope. So there's 5 types: M, S, C, H, and A. So these 5, right, corresponds to this one: mild, critical, steep, horizontal, and adverse slope. So from the name itself, right, you can roughly understand. So mild slope, right, means the water is slow, quote unquote slow. Okay, for a steep slope, then the water is very fast. Okay, so roughly you can like from the names, right, you can understand that. But to make it more concrete, right, the definition actually comes from what we have learned before, which is the normal depth and the critical depth. So these two, right, we will be using it again, basically. Okay. So if just for a recap, yn, right, is basically your normal depth calculated using Manning's equation. Is the q equals to 1 over n ARH half SO 2/3. Okay, then your YC, right, is from your critical flow equation. So YC is equals to Q squared over G 1/3. So again, this is just a recap. Okay, so from here, let's elaborate a bit more. So for a mild slope, right? For a mild slope, for a slope to be mild, your yn is bigger than your yc. Okay, because mild, right, means deep and slow, deep and slow. Okay, so this indicates, okay, this is yc, right? For example, this is yc, and this is yn. So this is a mild slope. It is a mild slope, or M. So again, just to relate it to the topic that we've learned before, right? If you remember the EY diagram, so this is Y, this is E, and the diagram looks like this. And this is your YC. So for any flow depth which is higher than YC is what we call the subcritical depth. Anything below is the supercritical depth. So for mild slope, it basically says that the normal depth is a subcritical depth. Okay, so remember the EY diagram is for any depth. This one we specifically say that it's the normal depth. Okay, so the normal flowing water, right, is already subcritical. Okay, so that's what mild slope means. Okay, so the normal depth is subcritical. Okay, hello, incoming. Okay, and then next we have the critical slope. So this one is yn equals to yc. Okay. Then for steep, yn is less than yc. Okay, just to give you a, so this one is a steep slope. S. So imagine this is your yc. This is your yn. So it's below. So that's how you differentiate the two slopes. So for mild, the normal flow is deep and slow. For steep, the flow is very fast and shallow. Okay, so again, it's corresponding to subcritical and supercritical depth. Okay, this one is just a critical flow. Okay, so I hope now you can differentiate the types of slope. There are actually two more types of slope, which is the horizontal. From its names, horizontal slope means the slope is just 0. Okay. And for adverse, right? For adverse slope, the slope goes upwards. So it's a bit weird, the slope goes upwards, not downwards. So that's what we call the adverse slope. So for these two cases, there are no normal depth. Okay, there are no normal depth for these two cases. Why there are no normal depth? Because again, if you go to the definition of normal depth, it means it's the quote-unquote normal flow when there is no obstruction. Okay, can you imagine? There's no obstruction. The flow is what we call the normal depth. So for a horizontal slope, right, there's no way for the water to flow unless there's an external force or there's a change, correct? So that's why we don't have a normal depth here. Because there's no like quote unquote normal condition. The flow cannot just go by itself. The same with adverse. Okay. So for horizontal and adverse, there's no normal depth. The flow is always changing. So it's not a straight line. And it cannot be a straight line. Okay, so that's for horizontal and adverse slope. However, there is always a critical depth, because critical depth, right, by definition, basically means the changing depth, okay? So the threshold is always there, but the normal depth is not there for horizontal and adverse. Okay. Okay. So for the second part, right, it's actually a continuation from the first part. Plot the critical and normal depths. Now you know how, right? So yeah, so for mild slope, you plot it like this. For steep slope, you plot it like this. Okay. Yeah. Okay, so far it's just very basic stuff. Now let's go to the next one. So this is again a continuation of the one before. So if your flow, if your section is long enough, right, the flow will always go back to normal flow. So what this means, right? Again, let me go back to the definition. So for example, this is a mild slope, for example. So for a mild slope, YC is here, your YN is here. Okay, so if there's no obstruction, your what's it called? Your flow, right, is always on the normal depth line. Okay, but now let's say there's an obstruction. Let's say this is S. Okay, a steep slope. So for a steep slope, remember that YC is still the same. YC is still the same. But now YN is lower than YC. Okay, from the definition we explained before. So this is YN1, YN2. That is the boundary. Okay. Okay, so what this sentence means, right? So, okay, there are things happening here, right? There's like a curve here, a curve here. Okay, what this means, right? After this change, right? Whatever comes after it is always the normal depth. So that is what this sentence means. Okay, so if your section, right, if your stretch is long enough, the flow will always go to the normal depth. Same as the one before, like as the mild one. It always goes from the normal depth. So that's your benchmark. It always goes to normal depth when there's no obstruction. Okay. So far, so clear, right? Nothing hard yet. Okay. So now here's the fun part. So now we select the curves from this table. Okay. So there's a lot to explain now, but let's do it one by one. I guess let's start with mild first. So for a mild slope, right? Okay. So here's a mild slope. I'll be drawing this a lot of times. Okay, something like this. Let's say this is your YN. Okay. So now let's look at this table first. Okay, there's M1, M2, and M3. So what this means? What does this mean? So basically it means for M1, right? Okay, okay, the slope is characterized by one letter and one number. So letter and number. Okay, the letter indicates the slope where the curve happens. So if it happens in an M slope, then the curve will be M. It's that simple. Okay, the number indicates where does the slope go. Okay, where does the slope go? If it goes above, this is M1. If it goes to the middle, it is M2. If it happens below, like this one is M3. Okay, take note that it doesn't always start from YN. Okay, it only cares about which slope the slope happens at, and also the location. Okay, the boundaries, right? The boundaries of the number is the YN and YC. Okay, so if it's in this area, the slope is 1. If it's in this area, the slope is 2. If it's in this area, the slope is 3. It's that simple. Okay, so this is for M slope. Now, for another example, let's do S loop. So this S loop, again, YC is here. Oh, here. Okay, YC is here. And for S, right, YN is below. Okay, so similarly, so if the slope happens here, this one is S again, it's from the slope, and 1. Okay, S1, because it happens on top. Okay, it doesn't matter YN is above or YC is below. As long as the one is the one above, right, it's always 1. Okay, that's how we label the curves. It doesn't matter why YN is where, YC is where. Okay, top one means 1. Okay, then the slope here, for example, like this one is S2. Let me draw it nicely. Okay, like that. Okay, and then like this one is, whoa. Okay, this one is S3. Okay, so again, the letter depends on the slope. The number depends on the location. Is it top, middle, or bottom? Okay, top, middle, or bottom is divided by the yn and yc. It doesn't matter which one is on top or below. Okay, the yn and yc. Okay, but the boundary is this. Okay, okay, just to show you the table. So for for critical slope, the C slope, right? There's only C1 and C3. There's no C2 because logically speaking, right? Let's say this is your YC, this is your YN. So if your YC2 equals to YN, right? The two area, right, is like squish, right? So imagine this YC, this YN, right? But for a C slope, for a critical slope, YN is equals to YC. So the two is like squish. So there's only C1 and C3. Okay. This is just naming conventions, but you should know, you must know. Okay. Then for horizontal slope, again, there's no yn. Yn is infinity because basically the water cannot flow. Okay, that's why yn is infinity. So if yn is here, then yc is like here. So everything will be in H2, will be in the 2 area. One is above, one is to infinity already, it's gone. Okay, that's why there's only H2 and H3, there's no H1. Same with adverse. Okay, I hope the convention here is clear. So now, let's go to the rules, the actual rules. Just now it's just the naming conventions. Okay, so first things first, curves should not be allowed to extend beyond their own category. So what does this mean? So if you look at the example just now, the M slope and the S loop, and S loop. So let's say it's like, okay, it's like this, it's YC. So what this part means, right? Okay, if you look at how this behaves later, it's actually M2 like this, S2 like this. Okay, okay, explain to me why it's M2 and S2. Okay, so this YN2, this YN1. Okay, why is this M2? Because the curve is in this area. It's between YN and YC. That's why it's M2. For this one, the curve is, yeah, again, it's between YC and YN. That's why it's S2. Okay. Okay, what the sentence means this M2, right? It cannot go beyond the boundary line. So you cannot have something like this. You cannot have your M2 like this. This one is wrong. Okay, this one is wrong, yeah. So your M2, right? Your M2 cannot go beyond the boundary between M and S. Okay, if you draw it like this, then you got a problem lah. So this one cannot be like this. Okay, just to indicate. So so if this is M and S, is your critical depths. So M2, right, must stop exactly at the boundary. Cannot go extend. Okay, so that's the rule. It's just like that. Okay. Now, okay, here's the part that people get confused on. Okay, so here's the general principle of the water profile sketching. So for supercritical flow is what we call the upstream control. Okay, I don't know if your prof had mentioned this before, but I think he mentioned it quite a lot in my year. So yeah, so some people get confused with this sentence, okay? Then subcritical is downstream control. So what does this mean? Okay, this one you pay attention, okay? So imagine you have an M slope. Imagine you have an M slope. So M slope, right? YC is here, YN is above, right? So for M slope, this the flow is subcritical. Correct? Okay, now what subcritical has downstream control. So what does this mean? This means that for this particular section, it only cares about what happens downstream. Okay, for this particular box, right, it only cares what happens downstream of the section. So for example, we have a wait, what example is good? Okay lah, something like that, for example. Yes, it's the same example again. Okay, something like this. Okay, so okay, imagine you don't draw the water profile first. Draw this one first. So this YN, this YC. Okay. So again, M is a subcritical flow, so it cares on what happens downstream. So imagine you draw a box here, okay, for this particular reach of the river. The flow in this section is subcritical, so downstream control. It means you check what's downstream. Is there any condition change here? The answer is yes, right? The answer is yes. So there will be a curve here. So that's what this sentence means. So for this particular reach, you check the one downstream. Is there any change? The answer is yes, right? If there's a change, then there will be a curve. Okay, so what's the curve here? It's M2 because it goes from here then to here. Okay, then we can continue for the next one. So for steep, right? For steep slope, the flow here is supercritical. For supercritical, it is an upstream control. So it cares on what's happening upstream. So if we draw a box here, we check the one upstream of the box. So this one is downstream, upstream, right? So the upstream, right? Is there anything? Well, there is, right? There's a slope change. So there will be a curve on that side. So it'll be like this. Okay, there's a curve here. Downstream, right? You don't care. So it just goes to YN. So that's one example. I'll give you another example. So let's say you have a sluice gate now. Okay, something like this. So wait, let's say this is a steep slope. How should I do it? Let me check first. Okay, can. Here's a good example. Never mind this. Now let's say you have a reservoir with this. Okay, reservoir. Let's say this is a mild slope. Okay. So here's a mild slope. So this is the boundary. This is the critical flow. The critical depth, sorry. Okay, reservoir like this. Okay. So again, for mild slope, we are expecting the flow in this section to be subcritical. For subcritical flow, it's downstream control. So if you draw a box in here, we check what's happening downstream. So are there anything downstream? No, right? So if there's nothing downstream, then it doesn't care. It just goes YN all the way. No curve. Okay, so that's the key. If there's nothing downstream, it's automatically normal depth all the way. It doesn't matter what's happening upstream. So that's what downstream control means. So this one, it just goes directly. No curve. Okay, the key, right? If there's nothing if there's nothing downstream, it's YN all the way. So if you replicate the case, right, for a steep slope, so let's paste. So for a steep slope, right, then the flow will be supercritical. Supercritical flow is an upstream control. So if we draw a box here, we check what's upstream of the box. Is there any change? Well, there is, right? There's a change from the reservoir to the steep. So there will be a curve, okay, at the upstream, which is, wait, this one is from the top, right? So you're expecting to go down. So it goes like this. So this one is, it goes to YN, right? So above YN to YN, this one is S2. Okay. Okay. Okay, if you have any questions, just ask, or chat in the chat box. Okay, but anyways, okay. So now let's go to transitions. So for transitions between sub and supercritical flow, right? It depends on where to go to where. Is it sub to super or super to sub? For sub to super is what we learned before, is the choking. Okay. So choking, right? If you remember, the flow goes to YC. Okay. So for the cases that I've drawn so many times before, right? The M2S2, right? This one is the subcritical to supercritical flow. Sub to super means there's a choking, means goes to YC. So at this point, it must pass through YC. So that's a detail that we must take care of. Okay. Another example is if you have an M slope and you have a dam like this, or a actually no, let's do a sluice gate like this, something like this. Okay. So the condition here is subcritical, right? Okay. Right after the sluice gate, so imagine you have something blocking from top like this. Okay. Imagine you have this now. YC is here. So the sluice gate forces the water to go down below the YC, right? So if this is your grid, it's like this, then your water, even though it starts here, it is forced down here. So it goes out as a supercritical flow just in this part. Okay, understand, right? So it started as subcritical, but then because of this gate, the water is forced to go down like this into a supercritical flow because it's below YC. The opening is below YC. Okay, and then if you remember, right, this is a mild slope. So by right, if there's nothing here, again, it's a downstream control, right? Wait, let me check. Yeah, subcritical is the downstream control, right? So by right, in this section, we only care on what's happening downstream. If there's nothing downstream, then it should go back to YN. Okay? And you see, now there's a supercritical, here's the subcritical flow. So to transition from super to subcritical is what we call the hydraulic jump. So the transition will be, again, this one starts very low, right? So it must go up first. Must go up first. So this one is M3. Because again, why is M3? Because it's below YC. So again, the region is, again, this one is region 1, region 2, region 3. Since this is below, since this is the one below, right? So it's region 3, it's M3. And then hydraulic jump. So this one is hydraulic jump, goes back to YN. Something like this. So as you can see here, if we go from super to sub, it's always a hydraulic jump. Okay. What happens here, I'll explain in the part 8. So before any gate or dam, right? So there'll always be a type 1 curve, no matter it's mild or steep. So for this one, it's a mild slope. So again, this one is a dam, right? So it must be a type 1 slope. So this one is M1. The M1 goes up here. Because it's like, again, if it's a dam, right, then your water will be like stored at the back. That's why it goes up. That's why it goes to M1. Okay. It's similar to ponding too, like this one. But okay. 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 So let's give you another example. It's the exact same example, but now it's a steep slope. So this one is YC. YC should be higher, right? YC is here. YN is here. Okay, so again, if there's nothing here, right? Again, it's an upstream control, right? So for a supercritical flow, it's an upstream control. So if you draw a box here, you only check what's happening upstream. There's nothing, right? So it's YN all the way, quote unquote, YN all the way. So YN all the way from here. So this one is yn. But then if you notice, rule number 8 just now, right? Rule number 8, before any dam, it should be a type 1 curve. So if you remember, right, S1 looks like this actually. It's like this. This one is S1. Okay? So if you see here, there's a mismatch. This one is a subcritical flow. This one is a supercritical flow. Super to sub is a hydraulic jump. So there will be a hydraulic jump here and then S1. So that's how you check. Okay? And then for this part, again, this one forces down from below, right? So this one should be a, wait, actually before that, let's draw a box first. So here's a box. Okay. Again, this one is a supercritical flow. Supercritical flow, you check the upstream. It's an upstream control. So you check what's happening upstream. Well, there is something, right? So there will be a curve. So which curve it is? It starts below, right? So it's a S3. Okay. So yn, hydraulic jump, S1, S3. And you will see this pattern occurring again and again, actually. Okay. So yeah. The final one is this one, I think. Yeah, this one is the final one. So hydraulic jump. Okay. So for M, H, and A, right? It's always M3, H3, A3, then hydraulic jump. Okay. Means like this. So M3, hydraulic jump. Then like that. That's for mild slope or H or A. It's the same. Okay. It's always like this. So this is by C. Okay. Then for steep slope, right? It's always S hydraulic jump first, then S1. So it's the opposite way around. So for steep slope, it's hydraulic jump first, then S1. Okay. So for these ones, curve first, then hydraulic jump. For steep, hydraulic jump first, then curve. Okay, this is something to do with upstream and downstream control. That's why it's like this. Okay, so now that's done. Let's go to here. Okay, so now let's go to control points. So it's a point where there's a definite relationship between discharge and flow depth. So if you know the y, if you know the y, you know the q, and vice versa. So that's what we call a control point. So there are two types. So there's what we call the critical flow sections, or just simply gates. Okay, there are two cases where control points can happen. Okay, let me explain one by one. So I think it's easier to explain the critical flow first. Okay, because you remember, right? If your depth is YC, you can get the discharge from the equation YC is equals to Q squared divided by G 1/3. So if you have a YC, you can know the Q. So that's why we categorize critical flow depths as a control point. Okay, for the first part, for gates, it is quite simple. If you force the water to go down, right, like just now, this is M1, then let's say M3, hydraulic jump, and this, something like this. For gates, right, if you notice, right, you force the water to go down here. So since this space, right, is a fixed area, it has a fixed area, right? So you can know the so you can relate the Q to the Y. Okay, because Q equals AB, right? Q equals AB. So small q equals to BV, right? Wait, VY or BV? VYV. Oh, VY. So if you notice here, right, there's a relation between Y, and Q. Okay, that's why gates are considered control points. Okay, but anyways, I think an easier way, right? An easier way to explain this, right? But it's quite informal, is okay, quote unquote, the point you must go no matter what. I think that's the easier one. Okay, so for example, even though the water is like here, it must always go here, right? Because that's the only space available one. So that's a control point. So it's very simple. It must go down, right? So that part is a control point. This part is actually a control point also because it must go up no matter what. It's always M1. So that's a control point. So these two are control points. Okay. Then if we go back to this one, right? Mud and steep slope, M2, S2. No matter what, right? It must pass through YC, right? So YC is a control point. It's a point that we must always go no matter what. Okay. So that's another way to say it, lah. But yeah, that's very informal. Okay. So again, just some examples. So for a mild slope, again, you start here. And again, if there's a dam, it's always the one slope. That's why it goes up like this, M1. And this is the control point. Again, why is this control point? Because it must always go up there no matter what. So is that simple, okay? Same as this one, M2, right? This one is going to the supercritical flow, drops down like this. It must pass through YC. So this is a control point. It is a control point. Same as this one, and yeah, you can see the examples now. Okay. Okay, maybe let's do the examples and then we take a break. Okay. So just to give you an example first. So I have a lot of examples here actually, but I'll do the first two and you try the rest. Okay, while we take a break. Okay. So imagine like this. So you have steep, horizontal, and mild slope. So assume this is the YC. Okay. For a steep slope, YN is below YC. For a horizontal slope, there's no YN. For a mild slope, the YN is above YC. Okay. Okay, so let's start from the steep slope first. So for a steep slope, it's an upstream control, right? So draw a box at that section, check what's upstream. There's nothing, right? So automatically, it's always YN all the way. Okay, quote unquote, always YN, but later you see. Okay, so it's YN all the way. But then there's something here. Okay, it's the sluice gate. So it is forced to go up. Again, forced to go up. And again, what's the curve? It's S1. Because before any gate, it should be S1. So it's like this. And for a steep slope, it's always hydraulic jump first, then S1. So it's YN, hydraulic jump, S1, then control point. Okay. For horizontal slope, again, it's forced to go from below, right? So what's the curve? It's H3. Okay, because for horizontal, right, this is 2, this is 3. But it's forced from below, so it's H3. And if you remember just now, for hydraulic jump, right, it's always H3 first, then hydraulic jump. Okay, so if you go back, so it's H3, hydraulic jump for given value. Okay, and then mild slope, right? It depends on where the YN is. YN is always above YC, right? But it can be here, it can be here, depending on your calculations. Okay, assuming it's here, for example. So it will go up even more, right? So go up even more, it means it's H1. If your YN is here, a bit lower, if it's YN here, hey, there's no H1, sorry. It's H2. There's no H1, sorry. Then this one is just wavy, sorry, this one is just wavy. Yeah. If it's lower, then it's go H2. Okay. So depending on where your YN is. Okay. Something like this. Okay. Okay, so let's go to the next one. So draw your boundaries first. This is your YC. Okay, so for steep slope, right, your YN should be below YC. So it's here. Here's YN. For a steeper slope, your YN is even lower, right? Because it's even faster. So your YN should be below like this. Then for mild slope, your YN is right above like this, above YC. Okay, so now let's draw the water profile. So for steep slope, right, goes from below, upstream control, right? There's nothing upstream. And then for a sluice gate, it's always hydraulic jump S1, right? And then it's forced from below. Normal depth is here. So it goes to S3, okay? Because it goes from below, from the bottom portion, S3. Then steep and steeper slope, right? Okay, so let's focus on this one first. So imagine you have this box, right? Imagine you have this box. Again, for steep, right? Steep is a supercritical flow. It's an upstream control. So the curve happens upstream. Okay, downstream, there's nothing, right? We don't, sorry, it's not there's nothing, it's we don't care one. Okay, because again, supercritical flow only cares upstream. So if downstream there's nothing, it is just YN all the way. There's no curve. Okay, be careful, this one easy to get wrong. However, in the next section, right, for this section, now imagine you draw a box here. Imagine you draw a box here. Okay, for a steeper slope, the flow is supercritical, right? Supercritical is a upstream control. It only cares on what happens upstream. Is there something? There is, right? So there is a curve. So from here, the curve is S2. Then go like this. Okay. Next one we have mild. So here is a supercritical flow. Here's a subcritical flow. In that case, super to sub, you have hydraulic jump. Yeah, super to sub, you have hydraulic jump. Okay. So for this one, right, you have two possibilities. Can go like this, S1, or M3 hydraulic jump. Both are okay. So S1 hydraulic jump, M3 hydraulic jump. Okay. Then goes to here, and then here's a dam, right? So it goes to M1. Okay, I think we rest first. Any questions? Yeah. The S2 there got curved. When I say upstream and downstream, right, it only cares about one section. So, okay, now one by one. So imagine this section, right? There's an upstream control of this section. So for this section, the upstream is here, downstream is here. So is there anything upstream? There is. There's a change in slope. Yeah, so there is a curve. That's why it's S2. However, if we go back to the section here just now, again, it's still supercritical, right? Upstream and downstream control. Is there something upstream? Yes, sir. There's a sluice gate. That's why the S3 here. But again, it's the upstream control. We don't care about what's downstream. That's why here is just YN. Again? Yeah. Any questions? Yes. Yes. Oh, there's a hydraulic jump, is it? Oh, two possibilities. Oh, okay. Good question. Okay. Okay, the reason why there is a hydraulic jump in the first place, right, is actually because there's a mismatch between control. Actually, that's the reason. Okay, a bit confusing. Okay, I'll explain now. So for us, so for a supercritical flow, right? For a supercritical flow, okay, if you draw the box again, it's an upstream control, right? So upstream, downstream. So upstream, there's something, right? So there's S2 in this case. Downstream, we don't care. So it's just Yn here, correct? Okay, so by right, it should look like this, right? It's just S2, then nothing. By right. Understand, right? Okay, now let's look at the mild slope. Mild slope, is a downstream control. So up and down. Downstream, the curve is downstream. Upstream, we don't care, right? Upstream, we don't care. So by right, quote unquote by right, the curve should only happen downstream here. Upstream is just Yn, right? So now, if you notice, there's a gap here. And that's why hydraulic jump occurs. It's when the control have a mismatch, Understand, right? That's why hydraulic jump actually occurs. So mild, downstream control. So the curve is downstream. Supercritical, upstream control. So the curve happens upstream. So if both here is Yn, right, then what's this? That's why there's a hydraulic jump. You can actually try it out. Like even for this, right, it's actually because there's a mismatch. Okay, let me explain. Okay, so again, right, okay. So for this part, right, it's a supercritical flow, correct? For this part, right, it's supercritical flow. So supercritical flow is a upstream control. So the curve should be upstream. Downstream should be Yn all the way. But then we should go up here. So there's a question mark here. So what should we do? We add a hydraulic jump. Okay, good question. Because I didn't want to go there because I think it's a bit confusing. But now that you asked, okay, can. So actually hydraulic jump occurs because there's a question mark like this. Like it doesn't match, like the definition just now. Like the control, right, has a problem. Yeah. Okay, that's actually the key. Okay, good. Okay, so this one like this. Hydraulic jump S1. The same as this one, because there's there's a mismatch, right? So there should be a hydraulic jump somewhere. But steep to mild, right, is a special case. Okay, remember the steep to mild is a special case. It can be like this, can be like this. So hydraulic jump S1 or M3 hydraulic jump. Okay. So how do you know which is which? It's actually from the hydraulic jump equation. So this equation, this equation tells you which one is the actual case. So the one just now, right? I draw two. Those are the possible cases, but the actual case depends on the equation. Okay, I hope that clarifies. Okay, now let's take a break first, and I'll accept some questions first, because I know this one. But what you used to do, it's easy one. So you try the rest first, okay? You try the last seven. Okay. Let's take a break until like 803. Okay, 803. Um, oh, this one. Oh, because okay. So the logic, right? Let's start from here. Take control, curve is here. Right now we here, machine control sudah satu here. Now what we do? There's a mismatch. So there should be a jump. Hydraulic jump, two possibilities. Then hydraulic jump as one, and nanti ada jump. It's always with as well with and two. It's always with from hydraulic jump.
Then for the small part like the M1, like before we small as well.
Just it's steep, right? It will go up. Just again, this is a control volume. No matter the type of slope, it must go where. Yeah. Yeah. Once you do it, you understand. Just in case. Let's write it down first. Okay. So okay lah. Okay lah. Let's continue. Let's continue. Let's continue. Let's just finish this very quickly. Okay. So mild, right? Okay, mild. First things first. Downstream control, right? So this section, there's something here. So there's a curve. So the curve is from yn to the control point here. So this one is M1. Okay. Wait, I draw the normal graph first. Okay, and then for this part, right, it's forced below the YC. So naturally, it's just M3, hydraulic jump, normal depth. Okay, then mount to steep. So mount to steep, right? This should go to the control point, which is YC. Okay, because it's sub to super. So it goes this way, it goes this way. M2, S2. Then go straight. Okay, and then we have the critical depth here. So it should be normal depth is here, right? Normal depth is here. So steep, right, is um, steep is supercritical, right? Supercritical is upstream control. So doesn't care about what's happening below. Okay? Doesn't care about what's happening below. So there's a mismatch also here. I don't know if there's a hydraulic jump though. It's quite short. Yeah, I think can. Should be like this. Then this. Yeah, hydraulic jump S1. Yeah, because there's a mismatch, right? There's steep is upstream control, right? So the curve is upstream. So downstream, there shouldn't be any curve. Downstream, by right, there shouldn't be any curve. But then, since we are expected to go here, so there's a mismatch between here and here. So you must add a hydraulic jump there. Okay, then for critical, right? Again, this one is a control point before a dam. So this one is C1. Okay, C1. Okay, then this one is C3. Again, for critical, there's no C2. Okay, only 1 and 2. Because 2 is like squish. Okay? So it's like this. Should be wrong. Okay? Let's go to okay, done copying. Cheers, cheers. Okay. Yes. No hydraulic jump. Yeah, critical cannot have hydraulic jump. Because hydraulic jump is only to hydraulic jump is only supercritical to subcritical. Critical slope is just right in the middle. So there cannot be a hydraulic jump. Yeah. So that's why you just see one only. Okay. But critical slope is usually very rare because it's not good. Okay, it's not good because you modify it slightly, right? It can be subcritical or supercritical. It's very unstable. Okay, usually they won't test it, but I'll just put it here for fun. but anyways, okay, never mind. Okay, so mild slope, right? Yn is here, steep Yn is here, adverse no Yn, steep then Yn is here again. Okay, so mild, right, is downstream control. Okay, so if you draw a box, you only care about what's downstream. Okay, and the curve is downstream. So from the reservoir to the mouth slope, there's nothing. It's just transition like this directly. Then like this. Then downstream, right? There's something here. So M2. Steep slope, if you draw a box, again, upstream control. And the curve is also upstream. There is something, right? So that's an S2. Then like this. Okay, again, this one doesn't care, right? Because again, it's upstream control. But then you must go up. In that case, you need hydraulic jump. Okay, so that's what I mean. If there's like a mismatch, right, then you need hydraulic jump. Okay? I hope you all understand. Okay? So again, steep, right, is upstream control. So the curve is upstream. So by right, you can actually do this. But then you need to go up. So you need a hydraulic jump somewhere. Okay? Okay, so it's either S1, sorry, it's either hydraulic jump, then S1, or E3, then hydraulic jump. Okay, so it's hydraulic jump S1 or E3 hydraulic jump. Then steep, right, goes down, right? So this one is E2. Okay, and it must be E2. There's no normal depth, so it must be a curve. Okay, then like this, S2, normal depth. Okay. Can I? Okay, now let's go to it here. This one is actually even easier, I think, because okay, steep, right? Upstream control. Okay, so there's nothing, right? So yn all the way. So like this, yn all the way. But then A, you must go upward. So you need a hydraulic jump there. So it's not all the way, just stop here, hydraulic jump S1. Okay, and actually for the sluice gate case, right, it's always hydraulic jump S1. Either that or M3 hydraulic jump. Yeah, it's always that kind of. Okay, then mild slope, right? So M3 hydraulic jump. Because because we start down below, right? Mild slope yn is here. Okay. So you need something, right? So it's a M3 hydraulic jump. Okay, then mild, right? It's a downstream control. There's something there, right? So there should be a curve, like something downstream. So the curve is M2. Then S2. Okay, and then A, there's this one, right? But this case is exactly the same as this case. So you know it's hydraulic jump S1. So once you know, right, it's like reading. It's like you know the pattern already. Then if you ask to label the control points, here they are. It's on top of the sluice gate, bottom of the sluice gate, at YC, here YC, and here top of sluice gate, bottom of sluice gate. Okay, okay, same here. Okay, sorry. Okay, now let's look at this. So steep slope, draw a box as usual, draw a box. Then for steep slope, right, is upstream control. So you care what's happening upstream, and the curve is also upstream. Upstream of the box, upstream of the box. So here. Okay. So since it starts up above, right? So there should be a curve from going up to below. So the curve is S2. S2, right? Not S3. S3 is starting from below the YN. This one is between the YN and the YC. This one is S2. And then A, there's a mismatch, right? You need to go up, but here is YN. So you need a hydraulic jump. Hydraulic jump is 1. Okay, mild slope, right? Then this one is M3, hydraulic jump, YN. YN. And then for the lake, right, it depends on where your YN is. Okay, sometimes it's M1. If it's the lake is very high, it's M1 because it goes up. If the lake is like below YN, right, then it's M2. If it's somewhere in the middle, it's just wavy because it's not high enough for it to be M1. It's not low enough for it to be M2. So it just transitions very smoothly. So yeah, So that's what wavy means. It's just a local transition. Okay. What's high enough and low enough? High, I think, is just if it's higher, it's automatically N1. Low enough means the lake is lower than the YC. Because for M2 to develop, it must pass to YC. Understand, right? So if the lake is below YC, then there's M2. But if somewhere in between, right? So somewhere here, between YC and here, then usually it's just a local transition. Okay. Okay, this one you try yourself. I have the answer key, so you can look at it. But it's the same pattern. Should I do? Okay, let's do that. Just one. Okay. Okay, you start here, mild, right? Mild, you start up high, above YC. Then this one, right, you can treat it as a sluice gate. So again, you need to go up. So here is M1. But actually, this one is actually YC. Okay, that's the special thing about this. Goes to YC. While this sluice gate, right, this might not be YC. Okay, this might not be YC, but this is a control. Okay, but for this guy, right, it's always YC because choking. Okay, but anyways, so this one just goes down like this, right, very fast. So it follows the shape, okay, follows the shape. So it goes down below, right? So down below, then it's mouth, right? The mouth is downstream control. You only care about what's downstream. Okay, there's something here, right? So this is actually M2. But besides that, right, it's actually YN all the way. So there's a mismatch, right? So you need a hydraulic jump. So M3, hydraulic jump, then normal depth, M2, then steep, right? So it goes to S2. So M2, S2 is a very common occurrence. And then this one, right? Control point here. So you start down below. But steep is a upstream control. Steep is a upstream control. So by right, it only cares on what happens upstream. And the curve is also upstream. So if you draw YN all the way, there's a mismatch, right? If there's a mismatch, then hydraulic jump. This one and this. HJ S1. Okay, the pattern is always M3 HJ or HJ S1 is repeated. Okay, then go down like this, right? Go down below. Then steep, right? YN is somewhere here, for example. So this one, right? There's no hydraulic jump. It's just S3 like this. There, S3. Yeah. Okay, you look at this again. Okay, you look at this again and try to process it very slowly. Okay. Now let's continue first. Okay lah. Yeah. Again, if you're confused, go back to the rules. Okay. I know the rules are a bit boring, but once you try, right, you know what. Okay. 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 This one I think no time lah. So you try, This one tutorial line so you can see also. Okay. Okay. Let's go to hydraulic jump first. Okay. This one I don't know why for the past 2 years it's not tested the calculation. I don't know why, but I'll explain still because for me it's important. Okay. Okay, for hydraulic jump, again, if you remember, it's because there's a mismatch. Supercritical, subcritical. And then you draw the line, right? It doesn't match. So there must be a hydraulic jump. Okay? So when this happens, energy is not conserved. Okay? Again, there's a mismatch in energy. That's why it's not conserved. Okay? But momentum is conserved. Okay, momentum is conserved. So that's the difference. Okay, here's the equation. So for energy, right, the equation is E is equals to y plus q squared divided by 2gy squared, if you remember. Okay, you can review that, but it is energy. For momentum, they have their own curve, momentum curve. It's this guy. Okay, I don't want to go through the derivation. Okay, but it's this one. This one is not even that important. I'm just putting it there just so you know now. Okay, and when you plot this, right, it looks like this. Sorry, it looks like this. It looks like this. This momentum. So if you notice, right, the shape is actually fairly similar. Both are curves with noses. Okay, but if you notice hydraulic jump, right, it plots momentum, not energy. Okay, and between the two depths, it has the same momentum. But if you plot it again, right, to the energy graph, the energy is different. There's a change in energy. Okay, so two different curves, look similar but two different curves. Okay, so depths that have the same momentum is what we call conjugate depths. And be careful, right? There are two terms. There's conjugate depth, there's alternate depth, and these two mean different things. Okay, this is just so you're not confused. Alternate depth means same energy. Conjugate depths means same momentum. Don't confuse the two. Okay? Okay. So usually if you have a sluice gate, let's say you start here and go back here, right? Energy is conserved. Okay? So these two depths, so y1 and y2, are what we call alternate depths. Okay, alternate depths, not conjugate, alternate depths. But if we have this is y1, this is y2, this is what we call conjugate depths. Okay, so be careful. Okay, okay, so the only equation which is important for hydraulic jump is actually this equation. Okay, it's the equation to find the conjugate depth. Okay, it's y/2 times -1, all this. Okay, so something to take note, right? This equation works both ways. This equation works both ways. So it's basically saying if you know y2 and you plug it in this equation, so y2/2 minus 1 fr2, right? You will get y1. If you plug in y1, so y1/2 fr1, right? You get y2. So it's very convenient, okay? Just plug in one of them, you get one, like the other one. So it works both ways. Okay, you can try, okay? Okay, so what's the use of this equation, right? Oh, I think I have no time to go to go to the questions actually, like besides with the sketching, but I'll show you the use first. Okay, so if we go back, right, to our drawing just now, let's go back to this. Let's go back to this. So if you have wait, sorry, I think this one is easier. If you have a steep and a mild, right, there are two possible cases. Okay, goes from this depth, hydraulic jump to this depth, S1. Okay, or we can go up first from here, hydraulic jump to this depth. So how do you know which one is correct? Is it this one or this one? Okay, if you are asked to draw only, right, you can draw both, because both, right, are possible cases. But if you want to like chon, right, which one is like the actual real case, right? Then you need to know the numbers. Okay, and how do you get the numbers? It's from the equation just now. Okay, now I'll explain. Where is it? Okay, now, for example, you have a steep slope and a mild slope. Steep slope, mild slope. There are two cases, like this, then this, right? This. Or you can go down first, M3 first, then hydraulic jump, right? So something like this. Okay, you can either have M3 first or S1 first. So how do you know which is which? Now let's plug in some numbers now, for example. For example, this is 2 meters. Let's imagine, actually 2 meters will be good. Okay, but for simplicity, let's see 2 meters. It's very deep actually, but okay, anyways. Let's say this is 6 meters. Okay, just for example, 2 and 6. So how do you know which one is which? Okay, first things first, we need to identify the conjugate depth. Okay, this is the wait, let me label this y and 1, y and 2. So let's start with common misconception first. Okay, common misconceptions. Okay, so yn1 and yn2 not conjugate depths. They are not. Okay, be careful. Yn1 and yn2 are not conjugate depths. Second misconception. YC also not the conjugate depth. This is the most common mistake. Okay, conjugate depth. Okay, these are the two most common misconceptions there is. They thought yn1 and yn2 are the conjugate depths. They thought YC is one of the conjugate depths. The answer is no. Okay, they are not. So that's why when I draw the hydraulic jump here, right, I purposely try to not start from YC, because some people, they know this M3, right? They tend to draw it to YC, then draw the hydraulic jump. This is not always the case. Okay, it's not always the case. It's actually, right, it's an arbitrary depth. It's not YC. Then they go to hydraulic jump. So be careful when drawing. Actually, if you draw very quickly, you get YC, it's okay. But in actuality, right, it's not YC. Okay, it's not YC. Okay, be careful, The conjugate depth is not YC. Those are the two most common misconceptions there is. And even in the past papers, right, for CV2015, some people make that mistake. Yeah, so be careful, okay? So now I explain which are the conjugate depths. Okay, now you see here there are two cases. Okay, actually I wrote it here. This equation is applicable only right after and before the hydraulic jump. Right after and right before. Okay, so if we go back to this image, let's focus on this curve first. So the conjugate depth for this curve, right, is actually this one, 2 meters, with this depth. It's not 6, not this. Understand? It's only right before and right after the hydraulic jump. Okay, so it's somewhere between 2 and 6, not 6. Okay, so how do you get this depth? You know lah, it's from the formula. So you basically, if you want to find this depth, let's name this YA lah, for example, YA, literally YA. So YA is, then you go back to this lah. So okay, so 2 meters divided by 2 times -1 plus square root of, what is it? 1 plus 8 times the Prout number squared. This one you calculate yourself. This one is V over square root of G2. Okay, V you must find. Okay. Okay, because Prout number. Actually, wait, this is Prout number squared, right? So this one, the Prout number is V divided by square root of GY. So V is just V, you calculate V. This one is G times 2, because the depth here is 2, right? So you'll get YA. Okay. Okay. So that's how you get YA. So that's for the first case. Remember, that's for the first case. For the second case, I think you can guess already, right? How to get Y. Let's label this YB. So you know this part is 6 meters. The conjugate depth is, again, not this one, not this one. It's this one. This one is YB. So these are the conjugate depths, right before and right after the hydraulic jump. And that's why you need to draw the water profile correctly. M3, then hydraulic jump. So go up first. So this point, then this point is there. Yeah, okay. I hope you understand. So YB is 6 meters divided by 2. -1 plus square root of 1 plus 8. Prout number squared. But this time the Prout number, you use V divided by square root of G times 6. And the V, actually the V of the steep slope. This one is V of the, V of the mild slope. This one is V of the steep slope. because this happens at the steep slope. So use the velocity of the steep slope. Well, this happens at the mild slope. So you use the velocity of the mild slope. Okay, now let's say after you calculate this, right, you get YA is equals to, for example, 7 meters. YB is equals, for example, to 4.5 meters. For example, this one I don't use the calculations first. So if you notice, right, one case is impossible, right? It's always like this. When you solve this, right, one of them should be impossible based on the drawing. So if you notice, this one is 2 meters, this one is 6 meters. So YA, if it's 7 meters, it means it's here one. It's not according to the drawing. So this is not the case. I think that's the fake case, quote unquote. So that's how you know which case is actually the real one. Understand? So if you get YB equals 4.5, right, it means it is correct one. It is somewhere in between 2 and 6. So for this example, this one is the real case. Okay, understand? So what happens if you, for example, flip the Q, for example, then the other case is the one. Yeah? Okay, this one I don't have an example question for this yet. Actually I have, but it's not from 2020. It's from the it's before the course is called water resource engineering. It used to be 2 courses, hydraulics and hydrology. Yeah, they used to split this. Yeah, in the hydraulics module, right, they have this kind of question, like which one is the real one? Yeah, this is how we find the real one. I hope you understand now. Okay, so if this is the case, then this one is the real one based on these two. Okay, this one is the quote unquote fake. It's not fake or real, actually. Both are possible. It just depends on the condition, like your normal depths. It's just nice, that value. Okay. Okay, so I have 30 more minutes. How should we do? Let me see. I can cover this one also, actually. Just very briefly. Are you all confused with the steps, or you're okay with the steps? This one is actually just follow the steps. I just want to. I like to focus more on how to apply this than, sorry, when to apply this rather than how to apply this. So, okay, I'll explain when lah. Okay. Okay. So this one, it won't be answering the question also, but I said like won't be answering PYP, but I'll just explain when you use what. Okay. So I think let me search. Ah, wait, where is it? Calculate the distance between the intersection of reaches 2 and 3 and the location where the hydraulic jump forms. Okay, so if you look at this thing, right? Okay, I assume, right? This one is a steep slope, this one is a mild slope. Okay, you can calculate it using YC and YN, but I'm not going to do that here. I just assume this is steep slope, but you can actually count. Okay, for example, like this, then steep slope. So again, steep slope, right? You start down below. Mild slope is up above. So you have 2 cases, hydraulic jump, S1, or M3, hydraulic jump. Okay. Correct? So I think in the previous question, they asked you which one is the real one, right? Will a hydraulic jump form in reaches 2 or 3? So that's the exact same question that I posed just now. Is this. Okay, you check the conjugate depth values. Okay, and check which one makes sense with the drawing. Okay, basically. So okay, now let's say you know that this one is real. Okay, let's say this one is real. Now you are interested. just now the question says, where is the hydraulic jump is, right? So it's asking, what's this distance? So that's the question. Okay, understand, right? So it's asking the location of the hydraulic jump from the intersection. So it's asking this x. Okay. So again, for direct step method, right? So for direct step method, your input is R, Y2, and Y1. Your output is your distance between Y2 and Y1. Okay, I'll let you know the input and output first. There's also another method, right? I forgot what it's called, but it's the other way around. So you give the distance, you give the x, they will give you the y. But for direct step method, we give them the y, they will give us the x, the distance. Okay. So that's direct step method. One assumption of direct step method, I'll just write it down, is the channel must be prismatic. Okay, means if it's a square, then the bottom should be a square also. Okay, cannot change shape. Cannot like this one is rectangle and suddenly becomes trapezoid. Cannot. So it's only applicable for prismatic channels. Okay, but most of the case, we only care about prismatic channels. So usually we can use this direct step because it's easier than the other method actually. Okay, so now if you ask what's the distance of the hydraulic jump, right? I think it's clear which values you must plug in, right? I hope it's clear. Huh? We are finding the distance between this, right, and this. So the 2y that you must use is 2 meters and YB. Again, the common mistake, right? People use 2 meters and YC, the critical depth. No, nothing to do with critical depth for hydraulic jump. Okay, for hydraulic jump, we only care about the conjugate depths. Okay, critical depth is outside the equation already. Okay, so if you want to find this x, you must plug in 2 meters and YB to direct step method. And oh, one more thing. I think for direct step method, you need y2, y. Okay, the input is to y, right? But you also need some parameters. I think you need the slope. Yeah, SO. So what SO do you use? Well, we're finding the distance at the mild slope. So we use the slope of the mild, not the steep. Okay, because the real case happens at the mild slope. So what happens if the case is the steep slope? Then you're finding this x, right? Basically, you're finding this x. Okay, if it happens at a steep slope, then you're finding this x. So you need 2 meters and YA. If sorry, yeah, sorry, not sorry, it's not 2 meters. Sorry, it's not 2 meters. It's okay. If this is the real case, then it should look like this, right? Should look like this. So the y here is 6 meters. Okay, then the hydraulic jump happens here, right? So you're finding YA. So 6 meters and YA. That's your distance. Okay. Okay, so I don't think this is, I don't know if suddenly this is changed, but this is yeah, this is just to give you an idea on where to use these equations because it's in the lecture, right? Yeah, so yeah, I hope this clarifies on what's happening in the tutorial and the lecture. Okay. Yes, I think most people don't know about the case 1, case 2. So I'll just explain it here. Okay, and I think that's all actually. So I think the rest of the time, right? I think I'll just answer the questions that we have. But if you don't have, then I'll just do one of the questions here. So yeah, is there like any particular questions you have? Or you just want to do like past paper? Past paper. past paper. And should we do this one or the CV 2020? Because CV 2020, right? I don't think they have calculations on hydraulic jump, but they do have the sketching. Yeah. For the past 2 years, there's no calculation of hydraulic jump, but I just put it here just in case, because it's in the lecture notes, it's in the hydraulics course. But for some reason, CV 2020, they never include this. For some reason, I don't know why. They only include it until water profile sketching only. Yeah, okay. Okay, I think it's a good idea. Okay, I can lah. Let's go lah. So wait, let me let me open NTU library then. NTU library password. Oh yo. Okay, so CV 2020. I think 70. Okay. There we go. Okay. Sorry, this one I not prepared because okay. Okay, this is the most challenging paper for CV 2020 for the past 2 years, in my opinion. Yeah. Okay, so don't be surprised one, but no, it looks terrifying. It looks terrifying. That's why when this came out from last year, I was teaching this model also. I was like, holy smokes, okay. But this is actually a very good example on, okay, because if you notice, right, usually final question, you have 2 questions on hydraulics, 2 questions on hydrology. For this paper, I don't know why for this paper, 1 question for hydraulics, 2 for hydrology. And this 1 question, right, it's connected. One to J, I think. Oh, okay, but anyways. One question. One question. Yeah, actually, I used the like the one in this one is from last year lah. That's why I just copy paste. But I think for this one, I'll just send you the solutions. Yeah, but anyways. 3 questions. Yeah. Yeah. Okay, so it does look terrifying, right? But let's analyze it one by one, okay? So you're given a reservoir. That's spillway, that apron, something. Okay, but anyways, let's just go. So you're given, okay, this one is, okay, I'll just label CV 2020, question 1, 2022-23 Yeah, I don't know what happened that year, but okay, now you're given the crest length of spillway is 30 meters. Okay, and then the flow depth at the crest, right, is 0. Okay, so flow depth at crest is 0.15 meters. So find the overflow discharge per meter width. So discharge per meter width, right? So discharge per meter width. Oh, and then show, okay, yeah, sorry, show, yeah, so find small q and show that q is 5.5 meters cubed per second. Okay, this is part A. Okay, so let's analyze this. So the spillway, right? The crest length of the spillway is 30 meters. So actually, right, what this means, right? This is your spillway. This length is 30 meters. Okay, that's what we call the crest length. The y crest means the y at this, right? So this y is 0.15 meters. Okay. So, and this is reservoir, right? So reservoir means the water is here, reservoir. Okay. Okay, now you need to find small q first. Okay, so this one is actually a concept question actually. Okay, remember if you're going from reservoir, remember that in the crest, right, the flow is super critical. Because you just imagine you're going down a slope, right? So the water flows very fast. So logically speaking, this is very steep slope you can consider. So reservoir is very big and deep, right? So it's technically a quote unquote subcritical condition. Okay, so this one is subcritical. So subcritical to a supercritical condition means it must pass through YC. So 0.15 is actually the YC. So it needs some needs some concept, okay? So if you remember, right, YC and Q is related directly. Again, it's a control point. It's related directly. So it's a control point. So YC is equals to Q squared divided by G 1/3. So if you rearrange this, you will get Q is equals to square root of YC to the power of cube and G, like this. Okay. So in this case, you have Q is equals to square root YC is 0.15. G is 9.81. So you will get Q equals to, I don't have my calculator, wait. I didn't expect to do calculations. Okay. Okay, 0.182. 0.182 meters squared per second. Okay, then now show that Q is equals to this. So Q is Q times B. Sorry, I got something wrong. 30 meters, not this. Sorry. So crash line is actually this. It's in that dimension. Because it's a dam, right? Dam is very hard, very wide one. So the water just go down, right? Can you imagine, right? So this length, this width is 30 meters. Yeah, okay. So B is 30. So 0.182 times 30. You should get 5.5. Yeah, 5.46 meters cubed per second. That's how you get it. So this one is a concept question. Okay. Okay. Can I? Okay, this one is like a review for quiz one, but I'll just give you a. Okay. Now here. So uniform condition, uniform flow condition, right, is observed in the reach BC and reach CD. Okay. Now you have this 6 meters. N is 0.015. B is 6. SO is either 1 to the power of -4. 1 times 10 to the 4. This one is the channel BCD. So if you look at the, look at BCD, right? It's actually this section. Okay, so it's a straight line. There's a drop, then it's another straight line. Okay, so let me draw it out. So this one is BC, and like this, then this. So B, C, D. Okay. Okay, so BCD has the following characteristics. Based on the discharge Q obtained in part A, show that, okay, you need to find all the properties basically. Okay, like all these properties you need to prove. So let's do it one by one. So Q here is 5.46, right? Meters cube per second. So for this channel, small q is Q over B, right? So 5.46 divided by B, which is 6. So 5.46 divided by 6. 0.91 meters squared per second. Then you can back calculate to find YC, right? Oh, and wait, never mind. Yeah, okay, Q squared divided by G. If you notice the YC here is different. Why? Like here, they have one YC, right? YC is 0.15. In the second part, they have another YC. Why is it? Correct, different B. Different B, right? So even though Q is the same, big Q, and so even though big Q is the same, the B is different. It's from 30 to 6. So YC is different. That's why you need to calculate again. Understand, right? Okay, so you'll get 0.91 squared divided by 9.81. 1/3. So you'll get, let me find. Okay, sorry, guys, I should have no, like put this inside the sheet, but I didn't expect this. Okay, you'll get 0.439. 0.439 meters. So it's according to this, 0.44. Correct, right? 0.44. Now let's find the minimum specific energy. Okay, so minimum specific energy, if you still remember quiz 1, it's EC. Okay, so EC is 3/2 YC. So 3/2 times 0.439. So you will get 0.658 meters. So same, 0.66. Okay, next one, uniform flow depth at each BC. So what's the YN here? So YN, you need to use Manning's equation. Okay. Okay. So Q is equals to 1/n times A times RH 2/3 SO half. Okay. Q is 5.46. 1/1 times 10 to the power -4 times area. Area here is, okay, this one is YN, right? This should be YN. So the area is 6YN, okay? Parameter is 6YN divided by 6 plus 2YN. Correct. So this times SO 1 times 10 - 4. Sorry, this one is not this. This one is 0.015. And then if you remember, this one you cannot solve. You must use solve function, your calculator. So solving for YN. Yeah, okay. Okay, never mind, not now. You can try it at home. 6x yes 6x divided by 6 plus 3x 2/3 1 times -4 to the power of half. I forgot the half. Here's with half. So you solve. Okay, the solution is what? 1.4, right? I'll just use 1.4 as a guess. Okay, never mind. This one, wait for the calculator. So yeah, there. 1.405. So quite close. Okay, so YN done. Okay. So now you get, oh, uniform flow velocity. Okay, so now find the VN, uniform flow velocity. So it's just Q divided by Y. Is it? Q divided by Y. Small Q divided by Y. Let me check. Should be this one. Okay, so small Q is 0.91 divided by YN, which is 1.405. So you will get 0.647. Yeah, close. Yeah, so they purposely round off to the higher decimal point, so you cannot like bluff. Okay, but anyways, specific energy at uniform flow. Again, you cannot use Q/2Y because it's not critical energy. You must use the full form. So the full form is Y plus 2 squared divided by 2gy squared. 0 is 1.405 plus 0.91 squared divided by 2 times 9.81, 1.405 squared. So you will get 1.426. So again, it's similar to the question now. Okay, so it's correct, okay? Okay. Okay, let's finish this and then let's call it a day, okay? Okay, let's go. Okay, now the steaming basin DE may be viewed as 0.5 meters depression after CD. So let's look at this. So there's CD and DE, right? So it's straight line, then there's a drop. And they assume it's a depression already. Okay, so CD to DE, right? You can assume it's like this. C, D, E. So this one assume as delta Z. Okay, it's 0.2, right? Okay, yeah, 0.2. Now, determine the uniform flow depth in reach CD. So find Yn here. Okay. So here's okay, you all know? Okay, so recap, so you need to find the uniform flow in CD. Let's go back here. Okay, here's BCDE. Just now we calculate for section BC. All these stuff that we've calculated is for BC. So how you find Yn in CD is it's not the energy diagram. Again, it's not the energy diagram. Why is it not? Because we're talking about normal depth. Okay, let me explain. Okay, so here's a trick question. I think most people get wrong. So we need to find the Yn of CD, right? Okay, let me draw the full image first. So like this, right? So BC, there's also delta Z here. So the question is, let's say we calculated Yn here, right? So Yn BC. Now we're finding this. Yn CD. So typically, right, if you have one Y and you want to find the other Y within a depression, you will do this thing, correct? Remember? Correct? Typically, you need to do this. However, this one is asking for normal depth. It's not asking for the depth right after depression. These two are different. Okay, so let me draw, right? If you draw the water profile, that's why water profile is very important. But this one is not something that I haven't taught you yet. This depression and hump or contraction is actually all what we call a local transition. It's considered under RVF alongside HG. So it's actually wavy like this. So if you put this inside the EY diagram, right? So if this is Y1, Y2 is actually this, right after. But remember Yn, the definition of normal depth is when there's no obstruction. When there's no obstruction. So it occurs way after the drop. Understand? It occurs way after the drop. So it doesn't care about the drop. It only cares about the Manning's equation. So as long as the properties SORHA is the same, right? The normal depth stays. Okay, lost. Understand? So okay, let me. So it's like this, right? Something like this. Normal depth here is the same as normal depth here because the properties are the same. SO is the same, N is the same, A is the same, RH is the same. Here, SO is the same, N is the same, A, RH. So even though there's a drop, right? So there is a change. Actually, yeah, there is a change in Y. Y1, Y2. But after a long time, right, it will go back. So that's a trick question. Because, okay, I'll go back to the question. Read part B. Okay, uniform flow condition is observed in reach BC and CD. this channel BCD has the following characteristic. So BC and CD has the same properties. So the normal depth should be the same, even though there's a depression. Okay, so if you draw the water profile, it should look like this. Okay, it's not enough for it to be M2 or S2 because how to explain? Because the slope is still the same like this. There's no like sudden change. Okay, the change is very small. Like if you change the slope, right, it's the change of the whole thing, you know. That's how you compare. This one is just a local change. So one is a global change, one is a local change. This one is a local. Okay, but anyways, let's continue first. Okay, now stealing basin DE may be viewed as 0.5 meters depression. So now estimate the flow depth downstream of D, some short distance into the depression. Now we need the EY diagram. You understand the difference now, right? So you compare this one. Okay, you compare the top sentence, the topmost. It says the vertical step between reaches BC and CD is 0.2 meters, right? Determine the uniform flow of CD. It's asking the uniform flow. It only cares about manning. So as long as your properties are the same, uniform flow is the same. Yeah, correct. But in part C, it's asking the flow depth downstream of D at short distance. So you need the EY diagram. Okay, I hope this one clear. Huh? Okay. Okay, but this one I think I'll just skip lah. Because I think you know how to do, right? Part C. Yeah, it's basically just this, and this. Delta E, sorry, delta Z. So this is Y1, Y2. Y1 is YCD. Y2 is the one we're finding. Done, right? Okay, next. Finally, we reached this one, the one that we just learned today. Okay. Actually, a lot, what? Okay. Okay. Part E. Okay, just this plus 2 and we're done. Okay. Produce a sketch of the flow depth downstream of D and at the M seal in relation. Oh my god. No depth in CD. Okay, they asked about CD to the normal depth just upstream of D. Okay, I'll just show you the solution because a bit long to draw. And I think it's, let me see. I remember I'm doing it. Okay, give me a second now. Yeah. This is what I explained just now. Okay, so this one, right? The spillway just now is like this. Okay, yeah, this is the one that we did just now. This is what I explained just now. So initially it's YN 1.41. Even though there's a depth here, right? It's just local change, then back to 1N. Okay. Then this one is the thing just now. Okay, this one I'll just explain. I'll just explain. So this one is just now is 1.41, right? Because of this depression, so we need to use this. Use this, we get 1.92. So 1.92 is the depth right after. Okay, right after. But then it will adjust back to normal depth. Okay, so is that okay? I hope you understand. Okay. So this is the drawing just now. Okay. I'll just zoom. Yeah, because no time to draw all the things. But okay. So when you draw the water profile sketching, if you have a depression, local transition, you can draw it as wavy. It's okay. Okay. Because there's no real curve to represent it. Okay. You can even draw it as a smooth like this, also can. Okay, but this one is not M2, not S2. Yeah, those things. But for this one, you must draw M1 because this is considered as it's high enough for it to be a spillway. Okay. M. This one is M1. This one I don't draw because it doesn't require. But for example, this is M, right? I think you know what's the continuation, right? M3, hydraulic jump. Okay. Okay. Then, yeah, this one we've done before, right? So, okay, I'll just end here lah. So, okay, wait, I'll just show the solution. Okay, these four. So the difference, right, is just the riverbank level only, and also the hydraulic jump. Yeah. Okay. Okay, I'll stop here lah. Okay, so please fill in the input form later in the file. But anyways, yeah. So you all can look at this one. And yeah, ask any questions. I think that's all for today. Thanks guys for coming. This one. Oh, okay.
It's okay, just I messaged the CE committee.
Oh.
Because I mean every other group mod will have this.
Oh.
You can manually add right?
Should be can. Yeah. Yes, I'll send the pass.
How about the solution?
Oh, this one C plus F. Okay, I'll send it.
Oh, she is not.
Oh, C plus F. Okay.
Then after the running
Ah,
I've been confused after the stop in the back.
Oh. Actually, I didn't do the calculations.
No, because I think you mentioned there was two Y values.
Two Y values, yeah.
How do we tell whether which is which like which one will fit what kind of curve? So I think you mentioned,
Oh, okay. The two options, right?
yeah, it was like something like this, like the
Okay.
two options.
Two options. Let me see. This one. Okay. C club later.
Oh, I go back.
Okay, bye-bye. Give me a second. Let me go back to the page. This one. Okay, so yeah, which part again?
Like how do you like if you get two values here, right? Then how do you know which
Okay.
fits?
Okay, I'll recap. So there are two options, right?
Okay.
So you can either use this as a conjugate depth, you get this. This one, you use this as a conjugate depth, and you get this. Because the values that we know is only 2 meters and 6 meters. We don't know these two. We don't know these two. So we get these two from these two calculations. So it's the formula doesn't. So from 2 you get this, from 6 you get this.
Okay.
Okay.
So we know, so like example in this situation, we know that 7 meters is not possible.
Yeah, because 7 meters is YA, right?
Mm.
YA in this drawing should be between 2 and 6.
Yeah, correct.
So if we get 7, right, then
It means it's rejected.
it's rejected, right?
Oh,
So
okay,
it's
okay,
not
okay.
this case.
Oh, okay, okay, I see.
Yeah. Okay. Yeah. Yeah. Well, this one, right, it is between 6 and 2.
Oh,
So that's the real case. So this one we don't need to, actually after drawing we can even erase. Because we know this one is the actual.
I see.
But if we don't know, we will draw it.
Then just one more question about the alternate depth.
Alternate or conjugate?
Conjugate I understand because of the drawing that you mentioned. Like this is alternate. Then so conjugate is just
Oh, it's hydraulic jump. It's
Oh,
hydraulic jump.
okay,
So
okay.
these two, right, are the conjugate depths. So if you see here, these two are conjugate depths. these two are conjugates.
Oh, okay.
Yeah.
Okay. So it's the before and the end of the hydrogen.
Jump. Yeah, correct.
Okay. Thank you
Okay.
so much.
Yeah, see ya. Thank you. Okay, I'll end the recording.